with flat earthers, and I try to help them, but I don't know. This was one of my first attempts at helping them see the curve that they keep asking to see. They're not interested, actually.
Yeah, this is James from Seattle. I'm the guy with the white beard on the bottom there. Not the big one, but the smaller one. And,
Hey, James.
yeah.
I'm Sean from Philadelphia, and I have the Jedi robe on, or the Sith robe, the Sith cloak, whatever you want to call it.
And I actually managed to screw this one up too. I think everyone's going to hear our entire conversation over the intro this time. Wanted to bring that gem out right there. You know, I had my finger over the button hovering, and like I said, sometimes the mixer either puts it at the above or below, and I can't control where it will put it. So it inserts this new one in, and I just went click. And I'm sitting there listening. Nope, no, it's even right. Totally wrong. I feel like a fool. But welcome, everyone. Oh, that was perfect. Yes. So, I know I almost want to play it again because I love that sound, because it's therapeutic. But okay, I'm just imagining it's the 124th time I've managed to, and I've only managed to screw up 20 of these. That's cool.
You're getting good at it.
Oh, you have no idea. I mean, when you go live, you're like, okay, no, I have it perfect. I just have to click this button, and that's fine. And then I keep forgetting it will jump. And so what I turned off the actual audio of the thing playing instead of us talking. So, brilliant move. Anyway, everyone, we're going to talk about GPS and hopefully not screw up too much. See how this goes. We have Jesse.
Woohoo!
Jesse from Philadelphia. Well, it's Philadelphia, I guess. So.
Actually, I'm in New Jersey, near Philly, and yep.
And he's a survey. Yeah, exactly. Sean's from Philly.
That's where I am right now. I'm going to go to work in about 2 hours too. So, yeah, I can see the Walt Whitman Bridge from my house.
That's cool.
Yeah, I'm real close.
So, yes, we're going to be talking about GPS and basically trying to come to terms with. This is more of a continuation that we've had to deal with I guess it's Professor Dave. And one of the next things on my list was building up to basically how GPS started. And obviously the theory of relativity comes before putting satellites in space. But the claim that it proves relativity came up. And of course, I had learned a while ago that, I mean, time is not into a factor. Basically, they're saying that clocks away from the Earth, no matter atomic or otherwise, apparently have a slight change, about 43 nanoseconds, if I'm not mistaken. And it needs to be accounted for. So they just set it on the Earth and flew them up into space at the appropriate altitude and left them there. But that's a layman's idea of what might be going on. I'd like to hear a little bit more. Now, you work with surveying, if I'm not mistaken, and well, you said so. And so you said, I'm not an expert, but I use a lot of the applications. So
yeah, I could tell you I've been a surveyor since 1978, and jumped into using GPS early on when it became available to us, and actually went to work for Trimble Navigation for a while as an instructor. Trimble hired a number of surveyors to come on board to actually do training in their software. And actually, do you guys hear me?
Oh, yes.
Okay, good. I was just watching on YouTube, so it was a little bit delayed. Yeah. So anyway, they sent me around the world. I went to actually Wuhan, China was one of the places I went. This was back in the 90s. South America a couple times, and then all across the U.S. Training people in how to use GPS in surveying applications and construction, yeah. So and so now I guess I should launch into what's my interest with the electric universe. I don't actually remember when I first what drew me in or what I saw first. I don't remember, but I would say
either.
it's.
I have a little.
I don't remember what it was that I saw. But as a result of just looking at some videos, and this is probably a good 3-4 years ago, I saw a video by Ron Hatch, and he was talking about GPS and how relativity is not part of what they're doing there to make it operational. In fact, he was pretty deeply involved in making it work the way it does, as I understand it. Anyway, I got drawn in, and I got very interested in that. And over time, I've looked at things like I don't know if you all are familiar with Nick of Time. He has a YouTube channel.
I think I have seen that. Yes.
And he talks.
I'm familiar with him too.
Yeah, it's on a huge channel. There's not a lot of views on those videos, but it's packed with great information.
Oh,
and I've
corresponded to that. So yeah.
Yeah. Corresponded with him by email, and also talked on the phone with him a bit. But so I'll just tell you, this idea I have is simply that. Before I talk about the idea here is that relativity is being employed in the operation of GPS, and you just see this all the time, that it's another proof of special relativity. And what I learned from Nick was that it depends on what you're talking about. And he says, and this goes beyond me in the math area. Okay, he's talking about Lorentz relativity.
Okay. That is a precursor to Einstein's special theory of relativity.
Okay.
And I might be wrong. So.
And then you have to pick a reference frame, and the ECI is what is chosen, the Earth-centered inertial frame. And when you align a special relativity to that same frame, voila, it looks like special relativity. But he says, in fact, it's actually Lorentz relativity that they're using to change the clock performance at those altitudes. And so it's cooked in, before they're launched.
Right.
And it works great. I mean, there's no disputing that GPS can give you millimeter precisions when done, when using certain techniques. There's a wide range of techniques to use the observables that we can record, that we can track from not only GPS, but of course the Russians have the GLONASS system. The European Space Agency has launched the Galileo system. So there's different constellations available to us. You can actually buy equipment that tracks all of those. And I think what we're discussing here would probably equally apply to all those different systems. And what's available to us is, like I said, a wide range of positioning techniques where if several meters is sufficient for your use, you may use just code phase observables. If you're looking for centimeter precisions, accuracy, I should say, if you're looking for that, then you're going to be actually tracking the carrier phase and doing carrier phase differencing. And that technique was really, people aren't aware of this probably, that was never really thought of at the initial planning stages of creating GPS. I mean, the military created GPS as a all-weather 24-hour day navigation system to guide vehicles and weapons and whatnot. So it was the guys at MIT who are the ones who do very long baseline interferometry, the tracking of signals coming from space at different observatories around the world. They employ a technique called carrier phase differencing, and they can get millimeter level precision differences in those two locations. And they've been doing that. Well, I don't know if that started in the 60s or 70s. I'm not sure.
Let's talk about that for just a second. Now,
yeah,
I just don't want to confuse anyone.
Okay, I just want to say that same technique, they are the ones who said, hey, look, if we put two GPS receivers out and record data simultaneously at two different locations, we can do the same thing that we're doing with VLBI. And that gave birth to relative positioning between two or more receivers. Okay, that's how that gave rise to the high precision applications that we use in surveying and construction, for many decades now. I'll pause there.
No, that's basically exactly what I wanted to know. Is basically because I could sit there and understand as an engineer what you mean by discriminating phases, or even phase cycles or being out of phase, but this seems to describe it better. Basically, from my understanding, then not just the satellites, but also other people can be used as satellite or as GPS towers, or is that what you're saying?
Other tower. What do you mean, towers?
Well, for example, obviously we're using satellites, but you said that it will give the option if we put more than one out to be able to balance between them, or otherwise get more accurate.
Let me clarify that. So there are three segments to these navigation systems. And the first, of course, is the space segment, which is the constellation of orbiting satellites, transmitting a whole series of information. I would encourage anybody that's interested in this, if you Google or search on GPS tutorial or GNSS tutorial, you're going to find so much information out there that will, you can delve into and learn about this. But I'll just in a brief summary here.
That's why when I saw that you had spoken on this with some authority, I was like, oh, okay, good, because I wanted to attack it, but I because I had already had this had heard that this was the case, and I've seen information to that regard, but I don't want to also sound like a fool, so I wanted to get at least the groundwork covered.
There's a good page there you have up now is the Wikipedia page, and so like I was saying, so you. Oh, go ahead.
Sorry, I think what Neil was saying when he meant people, when he meant that the handheld receiver is sending information back and relaying it to other handheld receivers. Is that what you were getting at?
Yeah, let me break it. Let me go into that. So you've got the constellation is one segment. Mm-hmm. You've got the ground control segment, which is operated by the Air Force in the United States for GPS, and then the other systems have their ground control. And what that is these installations around the world track the satellites and compute their orbits periodically throughout the day and upload new orbital information, continuously to maintain the system.
Basically corrections for the satellites.
Not corrections. They are sending their orbital parameters, the actual positions. In other words, those satellites are bobbling along up there. It's not a smooth thing. I mean, they're bobbling along, affected by gravity, and so you've got a broadcast orbit that we are tracking, and I'm jumping around a little bit. Let me get to the third users. The third segment is us, the users. So you got the constellation is one segment. The ground control is the Air Force who are operating the system. That's another segment. The third segment is all of us as users, from our phones to in our cars to, hey, if you've been driving along the highway and you see highway construction, and you'll notice on some of the bulldozers little antennas are on the blades. Agriculture today, a lot of the combines and huge farming equipment are being guided by GPS. So GPS is used practically everywhere, So we're the user segment. And so the way we use GPS, we're in a passive mode. We only receive the broadcast from the satellites. And you can, like I said, it depends on the cost involved in the equipment that you're using and the application that you're trying to accomplish. You may buy a very low costing receiver that is just going to give you several meters of position. There are ways of augmenting that to enhance it, but again, you are only receiving information. You don't send information back anywhere. So we're all receiving it. Now, in the survey world, I had spoken about, like the guys at MIT said, hey, let's do the same thing we're doing with VLBI. Let's take two receivers, two GPS antenna, and put them out here, and let's log the carrier signal itself. And back in those days, there were two signals transmitted, L1 and L2. Today, we have more than that. We have L5 and others, and we have all different kinds of codes being transmitted on these that can be decoded and used to form different combinations of observables.
Right.
The whole key there, to get down to centimeter level positioning, you have to do something that's called resolving the ambiguity of the number of cycles, okay? Because we know the wavelength of L1 and L2, we know how long those are.
Right.
What we don't know is how many waves came down before you turned on the receiver. So
wavelength
when you turn
is
that
the
on,
inverse of frequency, just in case anyone's paying attention to that.
so when you turn on the receiver, and it starts tracking satellites, it instantly can measure what partial wavelength came in, okay? So it knows it got 3/4 of an L1 wavelength, which is about 19 centimeters long. And but it doesn't know how many millions of wavelengths it traveled from the time of transmission.
Right.
And that is called the integer ambiguity. That is what is being solved for in the firmware or in the software that you're using.
Okay.
And that's what the MIT guys said. Hey, let's do that. And they, it's been very successful. So that's my little like summary of how GPS works. I've left out lots and lots of things, but just for the sake of time. But
well, don't worry. We tend to ramble anyway. So, but just then I mean, I have on the screen a little thing where there.
Some of us more than others.
Yeah. Well, there you are. But this is.
I have a question. I wonder, is it appropriate time to ask a question?
Oh no, go ahead. I mean, this is not a presentation or anything. I just wanted to know more about it.
Oh, cool.
From someone who knew more than me.
I'm really curious. Like
that's how dumb people learn. That's how we got there.
Like, yeah. And I, and just in the biggest sense of the, of the idea, it's wonderful that we have people from different disciplines coming to speak to us, because the whole idea, in my opinion, of the show is to bring different scientific expertises together to find that commonality in the electric universe. This is what mainstream science literally does not ever do. And so this is really one of our main aces in the hole that we can say, hey, let's talk about this. What do you think about how it relates to this? And that cross-pollination is just so, so important. So thank you so much for being. My question is this.
Gladly.
Go ahead. Go ahead.
No, go ahead. No, you have a question.
Okay.
No, you
My
go ahead.
My question is this.
No, you go ahead.
No, you go ahead. Bottom line is I'm curious about what are the most, what do people get wrong about GPS most? What are the fallacies? What are the old wives' tales, and what are the sort of like
that's a perfect
things
segue.
that we would not understand that you could help us to get? Like, what are the word
That's
That
a good
makes
one.
sense.
Yeah, no, good. It is good, and it'll help me remember to include a few more things that I haven't said yet. So in the just in the interest of being a little more complete. But I guess to answer your question, I think if it were you or maybe one of the others on this panel that said something about or thinking that we as the user send something elsewhere,
Right.
and that's not the case in the basic simple use of these satellite navigation systems, GPS and the others.
Just in case you're wondering, on the screen right now for anyone, there is a image of the Earth, a spot on the Earth, and at any time, there is enough satellites that, well, sometimes there's 10, but you can see the number of satellites that are visible at any given time from that spot. And well,
it's a nice graphic, yeah. And so yeah, we are not sending anything anywhere except for, now I'll tell you when we do. So in the basic use, no, we're not sending anything. We're only receiving. But in that basic use, and we're talking 90s, 80s, and 90s, we only could log data and then post-process it later. So we were always never getting a real-time answer. We logged that data between multiple receivers, and then put that data into software to then post-process the vectors, the interstation vectors, to come up with coordinates. And that's what we were doing as surveyors, is using these
locations of these satellites then based on the signal you're getting.
Well, what we were interested in is our location on Earth. We were putting these GPS receivers on top of a survey. Yeah, we're putting it on top of a survey monument or a point to be used as control for a mapping project or a construction project, this type of thing. And but you're right to bring up the point about the location of the satellites. The satellites are constantly moving very fast. They orbit the Earth twice a day, so they're moving quickly. What's being broadcast? Well, there's a lot being broadcast. One of the essential components is the navigation file. And that navigation file has in it the Keplerian orbital parameters that the software will use to compute the position of the satellite at the time of the transmission. So you have to know where the satellite was, what were its coordinates, and those coordinates are expressed or referenced to something called an Earth-centered, Earth-fixed Cartesian system, and those are X, Y, and Z coordinates in meters.
Right.
Now that reference frame is situated around the Earth, and with the origin being at the mass center of the Earth, 0.000 meters. Okay, so the software takes these positions that it calculates using the navigation file, and then performs intersections. Once you've solved for the ranges, and you need at least 4. These days we can track, 19, 20 satellites nowadays.
Oh, really?
Multiple constellations, yeah. At any one time, you're going to see at least 6 to 8 and possibly 9 GPS satellites. But if your equipment is one that also tracks, let's say, GLONASS, you're probably going to see at least 4 or 5, maybe more, GLONASS satellites as well. So you can track, a large number of satellites.
And just, I'll be very quick, just for people, basically this is, from my understanding of it, this is not unlike basically an extrapolation of what we used to do in surveying when you'd map a river in the, 1600s when you're coming up the St. Lawrence or something, and you have to use trigonometry, and you basically go from point to point, and you would be able to calculate using angles the entire coastline.
Yeah, that was called triangulation, and using theodolites, they would measure a series of angles to other locations, and then of course you'd have to occupy those locations and measure the angles back to form, triangles and quadrilaterals of sight lines. And then the only thing missing is scale. So on one of those triangles, you would have to measure the length. And then using trigonometry,
You can figure out the rest.
you can compute all the rest. Now that's a nice tie-in to what is GPS doing.
Well, that's what I was thinking. That's what
Yeah,
I've seen.
it's not so
basically-
much- Yeah, it isn't so much triangulation, although a lot of people say that. That would be one of the misnomers. It's actually trilateration. It is intersecting distances. Same thing, though. Same idea. You're going to intersect all these ranges, these lengths, from the XYZ position of the satellites to determine your XYZ position on Earth. That then is converted to latitude and longitude and ellipsoidal height. And then from there, we compute that or project that onto a mapping plane like state plane coordinates or universal transverse Mercator coordinates, or even some type of a local project datum where you assume 10,000 north, 10,000 east, in X and Y coordinates. And you can then relate it that way. So that's kind of the path, from space to us on Earth, and then putting that into some usable form, which brings it back to the mapping world, because let's face it, that's what we're interested in, is spatial relationships on some local project, whether we're constructing a rail line, a tunnel, a bridge, or a Walmart, whatever. Okay, so then here's the next thing that happened. That was in the 90s. We were logging the data, post-processing it later to get the positions. The next step here was, hey, if we could set up a GPS receiver over a known point and add to the system a means of transmitting what we're observing here over to where we are as the rover going around town, let's say. Okay. Well, that gave birth to a technique called RTK, real-time kinematic. And that just means, hey, we're out here moving around, we're kinematically surveying, and we're going to get our positions in real time. Well, how are we doing that? Well, the base station receiver has a radio hooked to it, and it transmits either over UHF or VHF radio the observables that are being logged at the base. So, so what's being sent is the base station name. Let's just say it's point 100. So we're saying, okay, point 100 and its position, that gets transmitted. And the raw carrier phase observables are being sent over these radio packets to the rover. So here I am, let's say I'm at the rover, I could be 10 miles away or 5 miles away. So I'm tracking my GPS signals where I'm located, and I'm getting a radio broadcast, slightly delayed, but practically near real time. And I'm getting the actual observables from the base. And so the computer inside my rover does the same thing that our software was doing in the 90s. It is now doing carrier phase differencing and resolving the ambiguities in real time and giving me positions right now. And that...
And more precise positions as well, right?
Well, they're the same as though I was doing it before adding that radio component to the system, when we were just logging raw data, and then we would post-process it with the computer later. It's giving me the same level of precision, nearly, to within several centimeters. But it's happening right now. So that, like I said, started in the 90s and was going on until this day with some additional developments. Today, we don't really have to set up a base receiver anymore ourselves. We can just gain access over the internet to a series of base stations that are set up permanently and are transmitting that data over the internet. And that goes by different brand names like VRS, Virtual Reference System, or the actual name of it is real-time network. So you're still doing this RTK technique, but instead of having to put a base receiver up someplace and leaving it there, which hopefully it's still there when you come back.
Right.
They use the internet, yeah.
We're using the internet. And so it's been economical too, because before I had to have 2 receivers, and one was pretty much stationary, just sitting over a point, and my rover could do the bulk of the work. Now I could take both receivers, hit the internet, gain access to, it's a subscription service basically.
Right.
So somebody is operating these systems, and so we're doing the same thing in real time. And I wanted to make sure I mentioned that, because anybody listening to this say, hey, you left off the whole thing about real time networks, and that's where we are today. And that's pretty much. Well, there's more. Then there's now RTX, and that is where.
Wow, I was about to say an RTX, because I know well, go on.
Yeah. Well, now you're getting your
whatever.
corrections. The corrections are happening instead of having base stations now. They have satellites that are transmitting the correction. Okay, so it's actually a spaceborne correction signal. And by the way, there have been many flavors of this over the years. The FAA had launched their own geostationary satellites that broadcasted a form of correction to users for aerial, for commercial navigation. And those are geostationary satellites transmitting a correction of sorts. And then that's a different technique, though. Instead of the one that I have been describing, instead of computing the ambiguities from the carrier phases, what in this differential technique, what you're doing is you have the bases that have known positions, and these are generally antennas mounted on buildings or they're permanently rigorous structures, and they're all over the world. If you want to Google and look up some of these networks, look at the IGS network. That's the International GNSS Service, and you'll see there must be thousands of these permanently installed antenna around the world. That's one.
Yep.
One of them. Unavco has probably also thousands of these, and they use it for crustal deformation studies.
Well, that makes sense.
Yeah.
Things are pushing up or down, or you're getting distension surface.
Yeah, and so with DGPS, differential GPS, which is used in marine applications quite a bit, and others, that technique is a little different. What you're doing here is these antennae have been surveyed in very precisely. We know the position of those antennas. Then they solve for their position using the pseudo ranges, and they're going to get a so-so position. It's going to be within several meters or better, maybe a meter to 2 meters,
Sure.
but basically wrong. And you'll watch that near position, which is wrong, is close, but you'll see it warble around. You'll see it going up and down and left and right. Well, what you're going to do now is make the assumption that you, as the rover, and you could be 50 miles away, the assumption is that your position is also wrong by the same amount. And so what they're going to do is transmit a correction from the wrong position to the right position and transmit that over a published format. It's called RTCM, radio time. You could look up RTCM. You'll see that's the broadcast format. And that is a very simple technique to just say, hey, at this instant in time, your position is wrong by this amount. Apply this difference. Boom, you've got a correction. That gets you meterish positioning, not centimeter. But it's good for lots and lots of applications. So,
like, help me, or anything like
yeah. So how about if I tell you what my idea was?
Well,
I'm really interested to see, and I get these grand ideas like, oh, this will be the once and for all test. Um, you know, you buy one of these Heathkit type GPS build it yourself receipt, kits that are like, I don't know, they're about $100, and just build a little kit. And then of course, we need some programmer. We need somebody who knows how to program. And then someone who can really read all of the high-powered math involved here and understand what Lorentz relativity is and understand what special relativity is, and then just do a test where you flip a switch. We flip a switch and we load. Okay, here's how it works right now, and it's working. We've got a known position here, and our system is reporting that known position, and all is well. It's working. And then we flip the switch from A to B, and B is going to be not special relativity. What happens? And that's I guess that's my kindergarten idea. I don't know if it's possible to do that.
well,
But
first we have to understand where the idea comes in. Now, and I could be mistaken, but from my understanding, it was known because, like you said, with Lorentz relativity, that there should be a decrease in time or something like that at a certain altitude. Now, this assumption could be due to any number of things. And how close was it to Einstein's guess, or was this even part of it? Like I said, this is where my confusion sets in, because obviously you can never really prove something, and this is the falsification part of science. But my question therefore becomes, how much was it even required to be considered? Because as far as I can tell, they basically just said it's going to be at this altitude, and they've flown at that altitude before, and they already knew it before they put the satellites up. So it didn't matter what it said; they were going to do with what it was. But I don't know.
yeah, I think you're speaking to how was it discovered, or hey, if special relativity is true, we better account for it. I'm not sure. I'm not up on the details of how that came about, but I do suspect, and I think that Ron Hatch was involved. They came to him for his assistance to solve the issue. And when you listen to him by the way, Ron has passed, and we can't go to him now with this. He passed last year. He was just about to publish a paper on this. He's published others on this. And
I can see as soon as I typed it in, Ron Hatch, gps.gov, boom.
And he talks about the fact that what we're seeing here is an effect on the clocks as a result of the gravity potential that they are living in and orbiting in, being so different than on Earth. And he that's what he's describing is, we're not seeing space-time warping. We're seeing an effect on a physical mechanism.
Yes. Basically,
and
in
it's
a
all
description, and I'm sorry, I'm very excited right now.
Yeah, no, go right ahead. Yeah.
The description that I often say, because people, obviously people in the Professor Dave area want to give an oversimplified and therefore straw man, and they crush it, But in this case, we're really looking for the details. You're talking about the rotation of electrons, which really don't rotate, and they're sitting there in clouds, and the way that they behave with each other and radioactive decay and all this other stuff seems to be different there. Now this, and this is what I seem to understand myself, is that the electrical potential could be the cause of all of this, because we also know that there is a problem that we're having with, for example, the solar decay, or the decay rates change depending on what part of a planet is facing towards the center of the galaxy. That's a very odd thing to never go away. and also prominences seem to affect decay rates. So here we are wondering about how this affects these type of things on Earth, and if it has something to do with the potential of the Earth, no matter what it is. But I would like to think that, and this is, again, one of the problems I have with the Einstein idea is you've mathematically described gravity in a different way than Newton did. But at the end of the day, you still didn't give us a why. You can't just say it magically happens. Like if I describe the flow of electrons and then say, well, and magnetism magically happens, I'm not really doing anything. I'm not, I mean, you have to solve that. And in this case, basically giving it a it feels that it gives a mathematical obfuscation to something that we should inherently try to figure out.
I think that the reason why it's convenient and easy to say, yeah, GPS proves relativity. I mean, that's just said, and people accept it and move on. They just, well, yeah, of course. Because it looks like it. That's one of the things that Nick of Time was saying to me on the phone. He said that, and by the way, he's well aware of some very high level conversations and correspondence between, the 20 people who figure all this stuff out. I mean, I don't know all their names, but there's a room somewhere where they turn the dials and make these things work. The simple
That's
thing is,
hot.
huh? Say that again.
I just got a visual of these like knights in the round table, with candlelight and like torches,
yes,
locking the doors and sitting down to have a conversation.
Yeah. So somewhere somebody figures these things out, and Ron Hatch was one of those people that they came to help figure out what to do, and they applied a clock correction, and it works. And then like everyone's happy, and we just move on. I just think that what we have before us is an opportunity to use a fantastically expensive laboratory that we didn't, it's there. We can track these signals all the time. So I'm thinking, that's why I put that post into the Electric Universe Theory Facebook group, was saying, hey, is there anybody out here that would be interested in, who has programming skills and the high math proficiency that I don't, when I look at this math on these pages, it's, I couldn't begin to pronounce it, but.
Oh, okay. Well,
what I bring is just experience in using the system, and could, be a part or participate in some test like this. And again, I have to say,
there's nothing
someone may look at this and say, nah, it's not possible. One of the things that has to happen is we have to go look at the book. I think you showed it a little bit earlier. It's the GPS Bible. It's 3 inches thick. It has all of the open source known information about how the system works. And it's going to have in there the equations on what they're doing to the clocks, to the satellites before they're ever even launched. So that will be a known thing. We can go see what that is. The idea here is that, if I understood Nick correctly, that the Lorentz method, the Lorentz relativity doesn't matter which reference frame you choose, it's still going to work.
Right.
But if you choose a different reference frame applying special relativity, things will break down. That's about as much as I know about that.
I think I know what you're talking about.
And if we could incorporate that into, this test, and write some software that uses method A and flip the switch to method B using the same data that we're logging right now, what happens? It would be a demonstration. Now, why go through that? Here's why. As you saw in the Facebook posting, the people that looked at it said, "Hey, I'm satisfied. I read this paper and makes sense to me." There's a bunch of papers there by people who refute special relativity being involved in GPS.
Right.
And that's going to reach a certain number of people. But a test like this one, I think, would reach a whole lot more, like thousands of surveyors, thousands of navigators who aren't really thinking about this right now. But if we could,
you would just you would basically just make it an app. Do you want to help science here?
But I'm saying if we could do this test and make a quick video about it, and it actually worked, and you flip the switch and you see the results right there and then. I mean, your position's going to be out hundreds of meters, or whatever that effect would be, by employing the method that they say they're doing right now, but actually aren't. What happens? And if that can be actually shown, how? I don't know, but this is the idea. If that could be shown, it would get a lot of notice, and someone would have some explaining to do. That's my idea. That is it.
Well, it's been my experience.
Bravo, by the way. Bravo.
Yes, definitely bravo. But well, I hate to say but, because that everything before a but apparently doesn't matter. But the thing I've tend to find out is that engineers build it, and it doesn't matter what we say. I mean, I'm not trying to be rude about that, but I think we had a conversation about that just the other day. Like, I mean, they're going to just say that it is because it's so easy to do, and it reinforces their sacred. I don't want to say Einstein is wrong or to chastise Einstein or something like that, because for some reason there's this. They put up this idea that we're all smarter than Einstein and we're all a bunch of, being arrogant when we shouldn't be. But we want to see something truthful here, and figure it out.
Yeah, I see that as well, and I'm more about just finding out what's real. That's exactly what I want to know. And so,
I've done my like share I said, of trig, like I can figure out a lot of this, but it's is time dilation even involved? Is there anything like this really happening? Can we and the trouble is that they can say it happens to regular clocks as well. Oh, it does? Let me know how many regular clocks you put in space with nanosecond timing, like Swiss nanosecond timing. Was that done? And if it wasn't, was it using a crystal like Timex? And if the effect is electrically transmitted, so to speak, or based on electrical principles or electrical density, at the surface of a planet or something along those lines, would the crystals that make these times not be affected as well as all the microprocessors that we put up there? Like there's so many questions now that I have to think about. And doesn't matter if it's shielded, like like that kind of thing. So clearly not, though. But
that's why we do this. More questions to ponder always. Hey, we got 53 people watching, Neil.
Oh, tell us more about them, Duff.
Are they being kind in the chat?
They are being, as usual, brilliant in the chat, because I am supporting their positive feedback and blocking them when they act like dicks. So that's how I roll. Hey, Doc Rocks is sorry about that.
That's
Doc Rocks says, could MEMS accelerometers be used? Could MEMS accelerometers be used?
That's not a question for me.
Okay.
I don't know what they are.
Doc Rocks, you're too smart for us, bro. Hey, Renegade says Carruthers is your math guy.
Yeah, I
would love to have him. I was really looking forward to meeting him at a conference that I had thought he was attending here in the U.S., but also Dr. Robitaille.
Well,
But
we'll
that
meet them
didn't happen.
both in 2021, I'm sure.
I hope so. I hope
They'll both be there. And I got the chance, and I'm not kidding when I say this, me and Robitaille and Carruthers had a wonderful chat sitting down at a table by ourselves at Hooters in in Arizona, and they had the greatest wings. But yeah, here I was. It was 2015, and I was just sitting there going, "Here these two guys are trying to convince me of their ideas, as if I was someone who was worthy of being convinced, you know, like as if I mattered." And they're like going, "No, you see, blah blah blah," and I'm like, "Man, they are totally into the truth. Like they. It doesn't matter if you were a rabbit, they would tell you all about it. You know,
I love it.
You know, and that's the passion.
If we had Steve Carruthers as our mathematician, and then we need somebody who can program, and for all I know, he does. I certainly don't. We need a programmer, and then we need someone like Nick of Time to look at the math itself and do the comparison of the Lorentz relativity, which, as I understand from Nick, that is what they're using, and that they've chosen the ECI as the reference frame. Then you've got to make a similar program, but it will be based on special relativity and choosing some other reference frame. And I don't know how far you'd have to go to cause a viewable, a difference that you could see on the display. And that's what I'm looking for, is an actual demonstration. Because to me, the 20 people in the room that are influencing the other 100 people that heard about it, and it reaches a number like 500 people, and then it reaches 1,000 people who they're not going to say anything about it because they realize what has just been proven. I'm not with this test I'm talking about, but with these papers, the papers that people have come out and said, hey, it's not special relativity, and here's why. And people are happy with that, but it isn't reaching everybody. And I think a test like this, when you flip that switch and you can demonstrate it, that's going to get notice. And the first people that are going to notice it are surveyors, because when you talk about passions, the passion of a surveyor is positioning.
Yes.
And he's all about getting it right and repeating himself and knowing that the work he did is reliable and can be used for whatever application he was hired to do, whether it's a boundary survey or, we're building tunnels under rivers. Whatever it is, we are driven to get it right and, using methods and procedures that are repeatable. And so that's the audience I'm looking to show that, hey, watch what happens when you actually do use special relativity. That's it. I probably have to jump off soon. It's Mother's Day plans that we have.
I plan on it for being a short
I've
show
got probably
for this
another
exact
5 minutes or so, and then I'll have to go.
I wanted to say
I have a quick question, if you don't mind.
Yeah.
So the GPS is in bulldozers. I've used one probably back in 2006 or 2005. I didn't like it, but don't the machines now automatically kind of grade for you based on the way the system works? Is that a question?
Exactly. It is called machine control. And what they were doing is trying to put surveyors out of business. No, I'm just kidding. We used to, what I'm saying is we used to stake out all that construction.
Yeah. Right.
And the bulldozer operator would look at our stakes and say, I better, I got to cut and fill here. And well, now what they do is that the GPS system is on the blade, on the grader blade, dozer blade, all types of different construction equipment. And in the display in his cab is the proposed design of the highway or whatever it is that they're building. And, he can either operate it himself, or they can actually do it automated, where he's just driving back and forth, and the blade is rising up and down, completely being controlled by the GPS. And another example would be in agriculture, where these giant combines are literally being guided by GPS back and forth through these fields to centimeters to within inches. Yeah.
Yeah, because I'm real old school, so I always used to brag about my fine grade skills and my contouring skills.
Oh,
I
did
see
you
the
do
stakes.
surveying? I'm sorry. Yeah.
Well, I have survey equipment at home. It's I haven't used it in years, but like cuts and fills.
I have an
especially
astrolabe and a Portuguese quadrant.
Cool.
Oh god, and again, like you're saying, the stakes are there. I really didn't need the stakes. I can get you within about an inch high or low, pretty much, which is really all we had to do in the environmental field. And like I said, once the GPS came out, it was only one time I was like, I don't really like this, but I heard, like, again, it's just really straightforward now, and most companies do use them. You see them all the time. You see them right on the front
Yeah.
of
Well,
the
let's
machines.
let's also recognize that you can buy this equipment and you can use it really wrong too. So there is let's give credit to the operators too, that are trained and know what they're doing, and make use
Trying
of
to get an accurate power equation on something rotating at 10,000 RPM. Okay, and trying to use the proof with a handheld voltmeter.
Yeah.
Now that right there, that's the type of stuff that people go, no, look, it's generating power because I'm getting more power out of here than I have over here. It goes, do you understand what power under the curve means and how wrong you are right now? And that the capacitors in that little handheld device can't even keep up with that, what you're doing. Anything past 300 hertz and they're toast. You need an oscilloscope. And this is what you mean by, or at least the same type of idea of wrong equipment will give you wrong ideas.
Well, just operating it incorrectly. Like, in other words, you can still make lots of goofy mistakes. You still have to have some expertise in what you're doing, and that applies to every field, I'm sure. So
then what you're saying is that, okay, like years ago, you could, as a supervisor, if my measurements, I'll call them, were wrong, say we're laying a gabion wall or something, and it's eventually going to be in water. One time I had to go back to a job site and get your book out, because there could be liquidated damages if you mess up an elevation. I'm like, dude, I went over 20 times. I was right, but it's like, there's you got to be careful with the doing it manually, if you want to call it that. But I've never used the GPS, so this GPS surveying is just going to be dead on. Is pretty much what you're saying.
Yeah, I mean, yeah. It is, and again, with the provision that it's like this. There's a thing called the data collector, which attaches to the GPS unit to record everything, and in there, you have a wide range of coordinate systems that can be loaded. You have the ability to calibrate your site to a local coordinate system. Those are the aspects where expertise is necessary to ensure that you're actually using the system correctly. But to your point, as it operates, as it's standing there, it is a reliable and will repeat those positions over and over to the level of precision indicated on the manufacturer's spec sheet. When you take that brochure and flip it over, it's going to tell you what you can expect that system to perform at. And I've tested them through the years in a number of ways, all in a wide range of tests, and I've always found these systems to perform just as the manufacturer states that they will. So yeah, that's
interesting.
Yeah.
No, you're very right.
I've never used it though.
I've seen some of these types of problems before, where you. But to your point, actually, one of the things I was thinking about is if you want to really make it as simple as possible, your test should be the minimum amount required, and not using any of the ones. We're not looking, basically the raw positioning, like the old school formulas.
Correct.
For like okay, we're going to use old school formulas. We put it on just a phone gets plugged in with one, and then you just plug it into a computer, for example, and you could read the data as it comes across, or anything like that.
Yeah, that's why I suggested one of these self-made kits. You can buy a user-built GPS kit. Maybe they're $100. I don't know, but
no. Yeah, I think we could do it even easier. I think we could probably just use telephones.
Well, not all phones are going to record carrier phase.
Well, no, but we're trying to remove the carrier phase. See, I know that sounds ridiculous, but if, in my opinion, and I could be 100% wrong on this, but if you're trying to convince someone, what you want to do is you want to say, here's the way it's written, okay, and here's the very base core of it. Here's not all the extra stuff like version 2 and just version 1.0. And this is how accurate it was within 15 meters or something. That's fine, because you're not trying to build anything with this. But the test is watching it go out of sync faster if it uses the relativity version or the Lorentz ones, and then just watch the circle of error grow.
There you go. Something along those lines. I think you're onto it. And again, part of this
that's a lot easier to program too.
It might need us to, like I said, look back in the document to find out just how much correction they do apply to the clocks, and then remove that correction to see the effect of that.
Right.
And then, there's going to be a few ways of looking at this or coming at it from different directions.
Probably learn a lot in the doing.
So I have to jump off. I'm going to leave you with a whole different thought now.
Okay.
And then I'm going to say bye-bye and check back with you guys later. So you got the IGS network. I think you showed it earlier.
Right.
You got this array of GPS receivers operating. These receivers sit there for decades. They are there to stay. Are we detecting a rise in the ellipsoid heights? Is it possible to use that to, as evidence that the possibility of the expanding Earth theory might be correct? I don't know.
I was wondering that because more than one person has claimed that, actually.
Okay.
Tantalizing.
We can definitely discuss that at a future time, perhaps.
And
maybe
again,
not on Mother's Day.
And that data's for free. You just go to the internet and tap in and get it and do what you want. It's just a nice laboratory to look at these things. Well, listen, Neil and everybody, it's been great. Thanks for having me on here.
Mr. Kozlowski, thank you so much for your participation. It was really
appreciate it.
Thank you. To get to know you.
Thanks.
I just like to suggest to you that you could do not just one or two things here. You use the raw data, and then see if you can't replace all the stuff that they use, the fancy math, with just plain math.